Hi everyone, welcome back to the channel. This video will be covering OCR A-Level Chemistry A, June 2024, Paper 2. If you do find this video useful, please give it a like and subscribe. Question 1 is, all organic compounds have covalent bonds. What is the electrostatic attraction in a covalent bond between? So this would be the shared pair of electrons and the nuclei of bonded atoms. B describes metallic bonding, C describes ionic bonding, and between two molecules, that would be intermolecular forces. Then question 2 is hydrogen reacts more readily with alkenes than with alkanes. Why is this? First statement is alkenes are polar molecules. Now this is incorrect because both alkenes as well as alkanes are nonpolar. Option B is all atoms in an alkane have a full outer shell of electrons. While this statement is true, it's also true for alkenes, therefore not a reason as to why one is more reactive than the other. Statement C is that the bond enthalpy of the carbon sigma bond is higher than the pi bond. Now, this statement is true and is also the answer to the question. So when alkanes react, it's the sigma bond that has to be broken, but when alkenes react, it's the pi bond that breaks. So if the sigma bond has a higher bond enthalpy, that just means more energy is required to break that bond, which is more difficult to do, thus making it less reactive. Then question 3 is a student investigates the rate of hydrolysis of different iodoalkanes using aqueous silver nitrate and ethanol. What color precipitate is seen? The precipitate would be silver iodide, and that's yellow in color. The structure of butanene is shown below, which row has the correct shape around carbon atoms labeled X and Y. So carbon X has 3 bonding regions, so that's 1 double bond, 1 single bond, and a third to a hydrogen. Therefore, it's trigonal planar. Y has 3 bonding regions, so 2 single bonds to carbons and 2 more to hydrogen, therefore tetrahedral. So we're looking at option B for this. Then question 5 is geraniol, shown below, is a component in many natural oils. Which pair of reagents identifies both functional groups in geraniol? So we can see an an alkene functional group and a primary alcohol functional group, which requires bromine water and acidified potassium dichromate. Question 6 is 4.3 grams of the alcohol C5H9OH is burned in oxygen. Which volume of oxygen gas is needed in decimeters cubed for the complete combustion of this alcohol at RTP? So RTP would mean we're looking at the formula, moles is equal to volume of gas over 24 decimeters cubed. Now looking at the question, we can work out the moles of the alcohol. So the moles of the alcohol would be 4.3 grams divided by 86, and that's equal to 0.05. Then the molar ratio looks to be a 1 to 7 ratio. So the moles of oxygen is 7 times this, and that's equal to 0.35. So if we sub in the values into the formula to calculate the volume, that's 0.35 times 24 equals to 8.4. So the answer is D. Question 7 is, which statement gives a valid scientific reason for global warming? Now, global warming is caused when infrared radiation gets trapped in the atmosphere due to the presence of greenhouse gases. So we can disregard C and D, and between methane and oxygen, methane's the greenhouse gas. So the answer is A. Question 8 is, the CFC, CCl2, F2, can cause the breakdown of ozone in the upper atmosphere. Which initiation step could occur with ultraviolet radiation to catalyze this breakdown? So the CFC looks something like this. So when you make a radical, you're either breaking the carbon-fluorine or the carbon-chlorine bonds. The bond that is easier to break would be the carbon-chlorine bond. Therefore, you're more likely to make a chlorine radical. Therefore, the answer has to be C. Question 9 is, which compound is a secondary amide? The first one is a tertiary amide. Option B is secondary, but an amine, because the nitrogen is not directly bonded to the carbon-carbon. So not that either. C looks to be a secondary amide, so that's the answer. Then question 10 is 1.35 grams of ethylamine gas is reacted with 20 centimeters cubed of 2 moles per decimeter cubed hydrochloric acid, forming a solution of ethyl ammonium chloride. What is the concentration of ethyl ammonium chloride in moles per decimeter cubed? So looking at the information, we can calculate the moles of the gas as well as the acid. And this is important because we have to identify the limiting reagent. So first, the moles of the gas. So that would be 1.35 grams divided by 45, and that's equal to 0.03. The moles of hydrochloric acid is 20 times 2. That's 0.04 moles. So the limiting reagent is the gas. So we use these moles as the product moles. Therefore, the concentration of the product would be equal to that mole value divided by the total volume, which the only volume we are given is 20. So we'll stick to using that. And that is equal to 1.5. So the answer is C. Question 11 is which compound could have produced the IR spectrum shown below? So on this IR spectrum, there's a deep absorption around 1700, and from memory, I know that that's a carbonyl carbon, and from the options, all of them are carbonyls, so we need something else. We can also see this broad absorption between 2500-ish to 3000, and on the data sheet, that broad absorption is carboxylic acids, so we can disregard A and C. And we have this absorption around 3,500-ish, so that could either be an amine or alcohol. I don't think there's no nitrogen, so it has to be the alcohol one, so option D. Question 12 is 1,6-diaminohexane reacts with hexane diol dichloride to form a polyamide and one other product. What is the other product formed? Now, this reaction is a condensation reaction in which this hydrogen reacts with this chlorine, therefore making hydrochloric acid. Question 13 is a sample containing a mixture of 3 components, X, Y, and Z, is analyzed using gas chromatography. The gas chromatogram below is obtained. The relative peak areas of X, Y, and Z are included. Which statement is or are true? First one is that the peak for X shows the mass of 1 mole. Now, we're not given that information, so I'd say that one is perhaps not true. There is a relative peak area of 1, but that does not mean it's exactly 1 mole. That's just relative to the other components present. So the first one's not true. Second one says that component Y stays in the column for longer than X, which is true because it's closer to 5 minutes for Y compared to X. And lastly, component Z consists of more than half of the sample, which is true because there's more of it relative to the other two. So that would be option C as the answer. 14 is the structures of 3 compounds, 1, 2, and 3 are shown below. Which compounds would produce the carbon-13 NMR spectrum with 2 peaks? First one has 2 peaks, so that one. Second one also has 2 peaks. Third one has 1, 1, 2, 2. So this one has 3 peaks, so not that one. So the answer is B. Now, for question 15, there was an error in the question, so unfortunately, this was disregarded from the exam. Then moving on to section B, question 16, which is about hydrocarbons. The structures of hydrocarbons A to E are shown below. Which hydrocarbons are unsaturated? That would just be B, D, E, as well as C, because benzenes have alternating double and single bonds in their structure. Which hydrocarbons are allocyclic? Just A and B for that. Not C, because benzenes would fall under the aromatic category. Which hydrocarbons have a general formula of CnH2n? So we're looking for alkenes as well as cyclical compounds with no double bond. Therefore, A and D. What is the systematic name for hydrocarbon C? So to name C, we start with numbering the carbons. Carbon 1 is given to the carbon with the highest carbon chain substituent, so the ethyl group. Then methyl groups on carbons 2 and 4. So its name would be 1-ethyl, 2,4-dimethyl benzene. And when you're naming it, also, the ethyl group should come before the methyl group as it has to be in alphabetical order. Question E is explain why hydrocarbon D is a Z isomer. So to be a Z isomer, the highest priority groups, in this case the methyl group and the ethyl group, have to be on the same side of the double bond, meaning the top half, or the bottom half rather, of the double bond. Then question 17 is about the reactions of alcohols. There are 4 structural isomers of C4H10O that are alcohols, which take part in many different types of reactions, including elimination, oxidation, substitution, and esterification. For each type of reaction, choose appropriate reagents and/or catalyst and show the organic product formed. So first we have elimination, that would produce an alkene, and for that we require an acid, such as sulfuric acid, or even phosphoric acid, but you cannot use hydrochloric acid because the chloride ions present may result in a substitution reaction instead. And the alkene produced would be CH3, CH2, CH, double bond, CH2. Next is oxidation of what looks to be a secondary alcohol. So this makes a ketone. And for that, we require acidified potassium dichromate. And the ketone formed would be CH3, CH2, C double bond O, CH3. Then is substitution of a primary alcohol. So you either make this into an amine using ammonia, or a haloalkane using sodium halide, such as sodium bromide, and an acid catalyst, so sulfuric acid again. And that would be CH3, 2CH, CH2Br. So just swapping the hydroxide for the bromine. Lastly is esterification. We have the alcohol, all we need is a carboxylic acid, so ethanoic acid could work, and an acid catalyst, so once again, sulfuric acid. And that compound would look something like this. Right, question 18 then, which is about haloalkanes that can be synthesized by reacting alkanes with halogens in the presence of ultraviolet radiation. An alkane reacts with bromine to form 2-bromo-2-methyl-propane. Write the equation for this reaction showing the structures of the organic compounds, name the reaction mechanism and the type of bond fission that occurs. So the mechanism would be free radical substitution, and the bond fission is homolytic fission. As for the equation, we know there's bromine present, and that reacts with 2-methyl-propane, and that makes the 2-bromo-2-methyl-propane. So just the hydrogen at the bottom being swapped out for bromine, and hydrogen bromide. Then it is to describe two limitations of the synthesis of 2-bromo-2-methyl-propane from an alkane and bromine. The first limitation is the fact that substitution can occur anywhere along the chain. So we want bromine in this position, but it could also have been over here, or even at the top. So that's the first issue. Second issue is multiple substitutions. So not just getting one bromine on there, but multiple different bromines. Also the fact that there's different termination products that could contaminate the desired product. So here's all of the possible answers that you could have written. Part B is to complete the flowchart by filling in each box. So first is bromoethane to an amine requiring excess ammonia, or ammonia and ethanol. And for the structure, it's just the bromine being swapped out for NH2. Everything else stays exactly the same. Then from bromoethane to an alcohol, that requires sodium hydroxide, or even potassium hydroxide, or even just hydroxide ions by itself. And that alcohol is, again, the bromine swapped out for a hydroxyl group. Then bromoethane to nitrile requires potassium cyanide and ethanol, but ethanol was in brackets on the mark scheme, therefore you don't require it to gain the mark. And then nitrile to amine requires reducing this triple bond through the addition of hydrogen and a nickel catalyst. And that would look something like this. Then from nitrile to carboxylic acid, that requires aqueous acid. So yeah, aqueous acid. And that would be CH3, CH2, C double bond O, OH. Question 19 then is about alkenes and carbonyl compounds that take part in addition reactions. Describe one addition reaction of an alkene and one addition reaction of a carbonyl compound. Include reagents and reaction mechanisms. Now this question is also marked by an asterisk, which means that it assesses quality of written communication. And that means your answer is marked based on levels. And to be in the higher levels, your answer will have to answer the question and also has to be well developed and logical. In this case, because it requires you to draw a diagram, try to make your diagrams as clear as possible as well. So to answer the first half on the alkene, that would be electrophilic addition for alkene. And an example could be ethene, and let's go with bromine. So those are the two reagents. As for drawing out the mechanism, so here's ethene, and that double bond will polarize the bromine molecule. So the top bromine is delta positive, the bottom bromine is delta negative. And this bond breaks via heterolytic fission, which would be useful to annotate because it helps with the quality of written communication part. And that forms a carbocation intermediate. It doesn't matter where you put that positive charge because it's a symmetrical carbocation or symmetrical alkene. and then to show that the bromide ion, the lone pair on the bromide, attacks that positive charge to make the final product, which is 1,2-dibromoethane. And you could also label the intermediate as carbocation. Then for the second half, which is the carbonyl compound, so that would be nucleophilic addition for the carbonyl. So let's use ethanol, and you could either reduce it or convert it into a hydroxynitrile, which is what I will do, and that requires hydrogen cyanide. And as for the mechanism, so here's ethanol. That carbon is delta positive, oxygen delta negative, and there's a lone pair on the carbon of the cyanide that attacks that carbon. And this double bond breaks towards the oxygen via heterolytic fission, and that forms an intermediate. And as far as I'm aware, I don't think this intermediate has a name, but if you do know it, please do put it in the comments. And that lone pair attacks the hydrogen ions present to form the hydroxynitrile. And the name of this hydroxynitrile would be 2-hydroxypropane, propane with an E, nitrile. Okay, that seems to be about it. Now, of course, you could have also used an asymmetrical alkene for the first half and shown the major minor product stuff and the different carbocation stability, because that would help with the quality of written communication, but that's by no means required. I mean, if you do want to show off your knowledge, go for it. But again, you have to think about your timing and that sort of thing. But this itself should be sufficient to gain the 6 marks, as it meets the criteria for that. Now, also thinking about it, hydrogen cyanide might not have been the best reagent over here. So this is a bit of extra information. It goes beyond the mark scheme, but you do need to know it. I think it's quite useful. So hydrogen cyanide is toxic, first of all, so that's not great. Secondly, because it's a weak acid, it dissociates very slowly, or to a lesser extent, meaning that you don't have enough cyanide ions in solution for this reaction. Therefore, this reaction has a very slow rate of reaction. So instead, something like sodium cyanide and acid would have been better, because it's safer to use. Sodium cyanide, being a salt, dissociates a lot more readily, so it's a lot faster as well. Again, not required to score the full 6 marks, but just good for you to know for like other questions. Then that brings us to question 20, which is about carboxylic acids and esters. Short-chain carboxylic acids, such as methanoic acid, is soluble in water. Explain with a label diagram how methanoic acid interacts with water when it dissolves. So first, to draw methanoic acid, so we're showing the oxygen-hydrogen bond, so the delta negative oxygen, delta positive hydrogen, and then a dashed line to indicate the hydrogen bond to a water molecule, which is also polar, and we're just showing that interaction. So this is the hydrogen bond. Then for part B, ester F has the structure shown below. What is the systematic name for this ester? So esters are made by alcohols and carboxylic acids. So when you write its name, the alcohol name comes first. So this would be the alcohol, and that looks to be a 2-carbon alcohol, so ethanol, which you write as ethyl. And the rest of it will be the carboxylic acid, which in this case is 5 carbons long, and there looks to be a methyl group on the 4th carbon. So this would be 4-methyl pentanoic acid, which you write as 4-methyl pentanoate. Question part 2 is ester F can be prepared from a carboxylic acid in 2 steps. Step 1 involves the carboxylic acid being converted into an acyl chloride. Step 2 is that acyl chloride being converted into ester F. Write equations for steps 1 and 2, show the organic compounds as structures. So first with the acid, that was 4-methyl pentanoic acid, so that would be something like this. And that reacts with something to make it an acyl chloride, so that something is SOCl2, and that makes the acyl chloride. And the byproducts are SO2 gas, as well as HCl. And that compound, the acyl chloride, gets converted into an ester, so that means we require alcohol, which was ethanol. So that makes the ester, and hydrochloric acid. Then for part C, the repeat unit of a polyester is shown below. Draw the structures of the monomers required to form this polyester. So here we can see the ester bond, it's this over here, So this would be the carboxylic acid, and the rest of it is the alcohol. So the carboxylic acid would be this thing with the benzene ring. Apologies for the drawing. And the alcohol would be this. In the next question, the compound below contains an ester and an amide group. Draw the structures of the organic products formed by complete alkaline hydrolysis of this compound using sodium hydroxide. With alkaline hydrolysis, you end up with carboxylate ions wherever there is a carbonyl compound. So to show which bonds are being broken first, we have this ester link that will break to produce an alcohol, which looks to be methanol, and that would end up with a carboxylate ion, so minus charge, and this would be the amide link that breaks as well, leaving you with a carboxylate ion as well. So to show that, the three compounds that are produced are methanol, and then this compound, well, not three then, that looks to be just two things. So hydrogen, two, and again, apologies for the drawing, it's quite messy, my skills are not that good. Right, so this would be the two carboxylates I form, as well as methanol. So now on to question 21, which is about aromatic compounds. Ethyl benzene can be prepared by reacting benzene with chloroethane in the presence of AlCl3 that acts as a halogen carrier. In this mechanism, chloroethane reacts with the halogen carrier to form a carbocation, which acts as the electrophile. What is meant by the term electrophile? Well, that simply is an electron pair acceptor. Part 2 then is to outline the mechanism for this reaction, including the role of AlCl3 as a halogen carrier. Now, AlCl3 is also the catalyst, therefore you must show that being regenerated at the end. So in the first step, to make the electrophile, AlCl3 will react with chloroethane, so CH3CH2Cl, to form AlCl4- and the carbocation. Then that benzene ring will attack the positive electrophile or carbocation, and that forms an intermediate, which has this horseshoe ring type of structure. And then this hydrogen bond will break inwards to form the product, as well as a hydrogen ion. Finally, that hydrogen ion reacts with AlCl4- to form the halogen carrier once again, and HCl. Then for the next question, Part B shows a table with the directing effects of different groups in the electrophilic substitution of aromatic compounds. Draw all organic products formed from monosubstitution reactions of the substituted benzene compound shown below. So first we have cyanide, which looks to be 3 directing. So we draw the same structure again, but on carbon 3 this time, we show chlorine. So cyanide takes the position of carbon 1, so here would be carbon 3. Then for the next one, this looks to be 2 and 4 directing, but we need to show monosubstitution products. So we draw one with 2 substitution and the other one with 4 substitution. So 2 substitution would be over here. And for the other one, it's the same thing again, except this time chlorine is on the 4th position. Okay, next question, part 2, is reactions of C6H5 and H2 are similar to the reactions of phenol. Write the equation for the tri-substitution of this with chlorine. So first we start with the initial compound, and that reacts with chlorine to form the tri-substituted product, so chlorine on positions 2, 4, and 6, as well as the byproduct, that is HCl. And to balance this, we need a 3 over here and a 3 in front of the HCl. Part 2 is to explain why chlorine reacts more readily with this than with benzene. Well, that would be due to the lone pair of electrons on nitrogen that get delocalized into that pi electron system that makes it more electron rich, and in doing so makes it more susceptible to electrophilic attack. So here's a written answer, and each bullet point is worth 1 mark. Then moving on to question 22, which is about alpha amino acids that have a general formula as such. The R group in an alpha amino acid contains carbon and hydrogen only. This R group has a molar mass of 91 grams per mole. A polymer is formed from 500 molecules of this alpha amino acid. Determine the molar mass of this polymer. Give your answer to the nearest whole number. So the first thing that we could do is to work out the MR of just one amino acid. So we have been given the MR of the R group. If we add it to the rest of it, which is a total of 74, the total for this amino acid is 165. Now if there's 500 monomers, we could multiply this by 500, and that's equal to 82,500. Now, this value is the mass of the polymer, but we're forgetting to take into account the water. Now, when you make this polymer, it's a condensation reaction, so water is removed. Therefore, we must account for how much water is removed and subtract it from this number. So if you imagine, if we have 3 monomers together, that's 2 bonds, and for each bond, a water is removed. Therefore, to find out how much water is removed in total, it's always going to be how many monomers there are minus 1. So then we could subtract 82,500 from 499 times 18, which is the MR of the water, and that's equal to 73,518, which is a whole number by itself. So that would just be the answer. Then question part B shows an amino acid that forms addition and condensation polymers. Draw 2 repeat units of these polymers, display the sections linking the monomers together. For the addition polymer, that requires the breaking of one of these double bonds to form these trailing or extending bonds to neighboring monomers. And to draw that, you can start with the 2 carbons that are part of the double bond and their associated hydrogens. For the second carbon, it's also to draw out this group that you could make easier by slightly shorthanding it. And this shows the first monomer that you have to copy out again to show the second repeating unit. For the condensation polymer then, that requires the formation of an amide link that's between the carboxyl group of one amino acid and the amine group of another amino acid. So if you're unsure about this, essentially, it's just that the OH of one amino acid reacts with the hydrogen of an amine group of a different amino acid, together forming a water molecule. So this is a condensation reaction, and that leaves behind a bond between the carbon and the nitrogen, which is a bit tricky to see drawing it like this. So to do it correctly, we could first start with the nitrogen, one of the hydrogens on it, and this is then connected to this group, which consists of a carbon, hydrogen, as well as this portion, that is CH double bond, CH2. And it's then connected to this group. Then you just have to copy everything out again to show the second repeat unit. Now, as for brackets, that was not required. On the mark scheme, it was also ignored, so whether you did the square brackets or the curved brackets, it did not matter. Then that brings us to question 23, in which the oil of wintergreen is a liquid used in medicine to relieve muscle pain. Compound H is a component in oil of wintergreen and can be synthesized from compound G as shown below. The boiling points and densities of compound H have been stated. A student prepares a sample of compound H by the method below. So in step 1, they reflux 8.97 grams of compound G for 30 minutes with an excess of methanol in the presence of a small amount of sulfuric acid as a catalyst. So essentially, they convert the carboxyl acid group on compound G into an ester through the addition of methanol. Then in step 2, they add excess of aqueous sodium carbonate and 2 layers are obtained. Those 2 layers would be water and compound H. So we know that water forms because when you make an ester, it's a condensation reaction, meaning that the byproduct would be water, and well, compound H, as that's the product. Then in step 3, they purify impure compound H that forms from the resulting mixture. The student follows this method and obtains 5.32 grams of pure compound H. Why does the student use reflux in step 1? Looking back at step 1, there's the presence of excess methanol. Now, methanol is an extremely volatile alcohol, so when it's heated, it very easily vaporizes. And if you want to keep it within the reaction vessel, you would have to use reflux conditions. So again, that's to prevent loss by evaporation. Then question part B, part 1, is in step 2, sodium carbonate removes the sulfuric acid catalyst and any unreacted compound G from the mixture. Write equations for this removal. So first with sulfuric acid, that would produce a salt, that is sodium sulfate, water, and carbon dioxide. Then for compound G, it's pretty much the same as the top reaction, in which you make a salt. Now, before I forget, it's only the carboxyl acid portion that reacts and not the phenol. So phenols are acidic, but they're very weakly acidic, so they're not strong enough to react with carbonates, but they are strong enough to react with alkalis such as potassium hydroxide or like magnesium hydroxide. So for this salt, it would just be the carboxylic acid portion. Phenol remains untouched, and we also make water and carbon dioxide. As for balancing it, well, that would just require a 2 over here and here. Then for part 2, Another student suggests that adding aqueous sodium hydroxide could be more effective in removing sulfuric acid catalyst than sodium carbonate. Comment on whether the student's suggestion is an improvement for the preparation of compound H. So the answer to that is a no, because of this phenol thing. So like I said earlier, alkalis like sodium hydroxide and potassium hydroxide that are stronger can react with a phenol. So it could also react with a phenol that is present on compound H as it's within the same reaction vessel, and we do not want that to be the case. Additionally, the presence of the alkali could also hydrolyze this ester bond, which again is not ideal. So that is no, because sodium hydroxide reacts with phenol and ester. Then part C is to calculate the percentage yield of compound H, give your answer to 3 significant figures. And percentage yield is calculated by doing the actual over the theoretical times 100. So looking at the data in the question, we have actual yield, that is 5.32 grams, but we do not have the theoretical yield for compound H. But we are given the mass of compound G, so we could start with that. First find the moles of compound G, and that's equal to 8.97 divided by its MR, that is equal to 138. So that's 0.065 as the moles. The molar ratio looks to be 1 to 1, so this would also be equal to the moles of compound H. Therefore, the theoretical mass of compound H would be equal to 0.065 times by the MR, that is 152. That's equal to 9.88. So then the percentage yield would be 5.32 divided by 9.88 times 100. That's 53.846, which to 3 significant figures is 53.8. Then for question part D, that is to describe how to purify impure compound H that forms in the 2 layers of step 2. So like we analyzed earlier, the 2 layers would be water and compound H. Now, we have been shown the density of H, and that seems to be higher than water. So within the 2 layers, H would be in the bottom layer. So what you'd want to do is put this into a separating funnel, allow the 2 layers to separate, and compound H would be in the bottom layer. Then you'd open up the tap, collect out compound H. Now, when you're doing this, it's possible that some of the water makes it through the tap as well. So to get rid of the slight bits of water that are present, you'd want to add a drying agent, such as anhydrous, calcium chloride, or even magnesium sulfate. Then once you do this, you'd have to redistill it at this boiling temperature to get rid of maybe any other impurities that would be present. Then finally, question 24, which is the last question. Analysis of an unknown organic compound J produces the following results. Here we've been provided with the elemental analysis by mass spectrum, IR spectrum, and the proton NMR spectrum. The numbers by the peaks are the relative peak areas. Determine the structure of compound J, showing all your reasoning. So I would start with the elemental analysis, and that's to find the empirical formula. So here's the empirical formula that I've determined by taking these percentage values to be the mass of the element, divided it by its MR to find the moles, and then divided each of the moles by the smallest mole number to get this ratio. And I've also found the empirical mass so that it can be compared to the MZ value of the molecular ion peak. And that molecular ion peak looks to be at about an MZ of 134, so it's the same as the empirical mass, which means that this empirical formula is the same as compound J's molecular formula. And this provides useful information, such as just having one oxygen in its structure limits compound J to either being an alcohol, ketone, or an aldehyde. And we can check which one by using the IR spectrum that shows the functional groups present. And the absorption that stands out over here is this one at 1700, which I know from memory to be a carbonyl group. There's also this absorption at about 3000. So if I look at the datasheet, well, it cannot be a carboxylic acid, as there's only one oxygen. Cannot be an amine or amide either, as there's no nitrogen present. Also, cannot be an alcohol or phenol, because we know there's only one oxygen, and that's part of this carbonyl group. So I'm just going to ignore that absorption for now, and move on to the proton NMR spectrum. And this shows us the hydrogen environment. So if we look at the first peak, which is a doublet, that has an integration of 3, well, that 3 tells us that this environment has 3 hydrogens, and the doublet means that the adjacent carbon has only 1 hydrogen. So this follows the n+1 rule, or in this case, it's more like the n-1 rule. I'm also going to color code that so you can see how the peaks and the numbers are referenced on the molecule. Then if we look at the next peak, which is a quintet, so splitting pattern of 5, well, that's at a chemical shift of 4, well, close to 4. On the datasheet, well, it cannot be a bromine group or chlorine group, and we know it's not carbon that's singly bonded to an oxygen, so I'm just going to ignore that second peak for now and move on to the next one, which is a singlet with an integration of 5. Its chemical shift sits between 7 and 8, and on the datasheet, that's a benzene. So for the 5 as the integration value means that there's 5 hydrogens in this environment, and this carbon has no hydrogen on it, according to the singlet, so it has to be bonded to another group. Then the final peak, which is a doublet at an integration, with an integration of 1 at a chemical shift of 9, well, that's the aldehyde, and that adds up. So the 1 is referring to this hydrogen, and the doublet refers to the adjacent carbon only having 1 hydrogen. So hopefully now you can see how everything fits together, as in this group will be the ending of this portion, and that also makes sense for the splitting pattern of 5. So if I were to rewrite that section again, so this 1 then, that's present, is for this hydrogen, and the splitting pattern of 5 are for these 4 hydrogens. And from there, we could also conclude that perhaps this benzene and its carbon is actually this one, which then fits perfectly together. So that could be the answer. So carbon, hydrogen, the aldehyde group, the methyl group, and the benzene. And we can confirm this by looking at how many hydrogen environments are present. So that's 1, 2, 3, and 4, which is 1 over here. That's the first environment. This is the second, this is the third, and this is the fourth. So this has to be the answer then. Now, as for how you put it together, it's the same as I have shown you. So start with the empirical formula, then do the molecular ion peak, then state what information is provided by the IR spectrum and the different sections of the proton NMR spectrum. I will also insert a picture of what the mark scheme shows you, so you can see how they've laid it out. And I don't know if you noticed from earlier, but this question was also marked by an asterisk, so it assesses quality of written communication. Therefore, it's just a reminder that your answer has to be neat, clear, and logically easy to follow. And that's pretty much it for the video, as this was the last question. So again, if you found it useful, please do give it a like and subscribe. Thank you for watching.